So we're getting ready to start a journey of how amino acids will marry and make these proteins for us. Well, the issue is that there's so many possibilities that these descriptions and this theory becomes complicated very quickly. So let's just take two amino acids. Let's take glycine and alanine. I'm just choosing those because those are our two simplest amino acids. Glycine has just a hydrogen as the R group, and alanine has a CH3 as the R group. So I'm going to take these two amino acids and I throw them into a flask, and let's pretend I want to make a dipeptide. So I allow these two things to hook up together. Well, there's a couple of choices that I could get. You know, it is true, I could have glycine, and that could hook up with alanine as I've drawn them here on the sheet of paper. So that is one dipeptide that I could make. However, you've got no control of how these peptides basically go and start forming up these dipeptides, polypeptides, and so forth. So you've got no control over these amino acids if you're not careful. So what would also happen is that maybe a glycine would hook up with another glycine, and maybe an alanine would hook up with another alanine, or maybe you could also get alanine that comes first, and then that hooks up with glycine. So if you look at these choices, you have at least four different dipeptides that could form if you started with two amino acids. Now think about if you threw a third one in. What would happen there? Or what if you threw a fourth one in? What would happen there? You see these number of choices exponentially grow. And that's the issue with proteins, because proteins, some of them have 40,000 amino acids that make them up. So just imagine for a minute, 40,000 amino acids. And if one of them gets mistreated, or if one of them is out of place, that could make the protein completely inactive. So the order of the amino acids are very important. And if I am given the task to make certain proteins in the lab, and I start off with some amino acids in order to do that, then I need some control. I need to kind of give some insight to these amino acids to kind of block them and protect them from reacting a certain way. And this goes into what we call N protecting and C activation. So most of the time when we protect amino acids, we are focused on the N terminus. And if we want to activate, means I don't want to protect it, I want it to actually react and do something, then this is really focused the majority of the time on the C terminus. Now again, we're not going to go into a lot of detail here. There's reactions that we can talk about, we can go through mechanisms, we can go through a number of things on this activation and protection. There's also more than one way to do it, but we will only really focus, for the most part, on one way to protect and activate these N-terminus and C-terminus on amino acids. Okay, so the reagent most often used to protect. So we're looking at N-terminus here, and that means protection. So we want to kind of cover it up a little bit. If we can protect it, then we don't really want it to be reactive. So one of the most common ones is something that we call di-tert-butyl dicarbonate. Okay, so let's break down that word and see what that structure really is. So di-tert-butyl. So I need a tert-butyl group. So CH3, CH2, 2CH3. That's typically the butyl group, right? That's butane. The problem though is that I need a tert butyl group. So tert means tertiary. So this is a butyl group. I need, however, a tert butyl. So a carbon needs to be tertiary. So that means it needs to be attached to 3 other carbons. So here is the tert butyl group. I still have 4 carbons in total, 1, 2, 3, 4, and this is a tertiary carbon here in the center, and that is why this is tert butyl. Okay, well, I need 2 of those groups, di-tert butyl. I'll draw the other one here in a minute. And then I see this word dicarbonate. So carbonate is basically going to be given to the structure of, dun, dun, dun. Let me draw it out here. This is an oxygen and a carbon, double bond O, and then an oxygen. So carbonate is CO3, right? That's typically what we learned in general chemistry. If something is a carbonate, it's a CO3 and it carries with it a -2 charge. Well, there's kind of the structure of CO3 there. So dicarbonate, does that mean that there's 2 of these? Well, in a way, kind of. So here is the oxygen, carbon, double bond O, O, and then that O is shared by another C double bond O, O, and then that's attached to my other tert butyl group. So yeah, it looks like a very long, complicated structure or reagent, but really it's not. You know, you look at this, and this is kind of our first carbonate structure, and this is our second carbonate structure, hence dicarbonate, and then this is our first tert butyl, and this is our second tert butyl, so hence di-tert butyl carbonate. So this is a protector group, and what happens is that this molecule will basically go on to the N-terminus of an amino acid, and it protects it. It doesn't want it to be reactive, so no reaction will go on. What happens is that it will sit onto the NH2 group, and this NH2 group, a hydrogen is going to be replaced. One of the carbonates will go on to that hydrogen location and carry with it the tert butyl group, and this basically covers up the reactive amino group as part of the amino acid. If you want to know what that structure looks like, go to your text, look at that section in the chapter. You know, this is 2210 if you're working out of the 7th edition, but if you're working out of another edition, again, older or newer depending on the year, then it's going to be in that range somewhere. You will see a section that will be titled N protector and C activator, and this is the N protector. So di-tert butyl dicarbonate. So this goes on to the N-terminus, and it prevents the N-terminus from reacting. So for instance, if we had an example of an amino acid, NH3 positive, carbon, C double bond O and O, and let's say that this is a CH3 for alanine. What goes on? I'm not going to draw the molecule here, but the molecule will come in and it will basically get rid of this positive and this some of these extra hydrogens. It will leave one behind because nitrogen needs 3 bonds in total, so it will leave one behind, but this di-tert or butyl dicarbonate will go on to this nitrogen and it will kind of sit here, and this protects it, and the tert butyl group is kind of large, so it kind of covers up that nitrogen that's there, and it protects this group from reacting. So what I'll draw here is just kind of an X over that piece of the amino acid to say that that is off guards. So that's the purpose of di-tert butyl dicarbonate. Alright, so there's one way that we can protect the N-terminus of an amino acid. In the next video, we'll take a look at the C activator. So we'll look at the C activator and see what happens there and what kind of reagent we need in order for that to happen. But you're going to see that they're very similar. So stay tuned, don't stop, at least watch the C activator before you take a break. These two kind of couple together quite well, so you might as well just suffer through the next 10 minutes. You ain't got nothing else better to do than to listen to me gab and talk on about amino acid structure.